All right, hello everyone. Today our topic, we're starting off by looking at segment relationships. So we're looking at how tangents, secants, and chords are all related. So first up, I've drawn us up a pretty picture, and we're going to see some familiar vocabulary. So first up, if I'm looking at a line, right, that notation means it's a line, and it's passing through E and P. So right here, I'm looking at that line. So I can see that it's touching the circle in one spot right here. So this is a tangent line, right? Just a type of line that touches the circle in one location. So a tangent line. And that point right there, that is the point of tangency. Okay, then if I look at EP, what EP is now doing, this is a segment, no longer a line, it's a portion of that larger line. So the portion is between here to here. So we're really looking at a segment that connects that point of tangency to another point that is outside of the circle. So from here to here, E to P right here, that is a tangent segment. Okay. So then I see my notation here, which is saying, oh, it's a line again. So here we know it's passing through E and K. So here's E, here's K, and it goes in two directions forever. So the fact that it has 2 points of intersection with the circle, that is a secant line. Okay, and then here we're seeing a segment notation. And it's saying, how about the segment from point E to point K? So it's asking from here to here. So this segment from E to K. So here what we're connecting is the outermost point of intersection with the circle and a point that is outside of the circle. So this whole portion from here to here, we call that a secant segment. And if I'm a little less formal in my language, I would call that the whole. You'll hear me say that many, many times. So again, this whole line is a secant line. It's passing through the circle in two locations. If I focus on a portion of it, so here this outermost point of intersection, along with a point that's outside of the circle like so, that is a secant segment. I'm going to call that the whole. Okay, I can take that secant segment and I can split it up into two parts. So I'm focusing on the part that is outside of the circle, right? That part is outside of the circle, and the part of it that is inside the circle right here. So next up, we're looking at ER. So we're saying from E to R. So I'm focusing on this portion of it here to here. This is the portion that is outside of the circle. So we call this an external secant segment. Right? It's the portion of the secant segment that is outside of the circle. So here, again, if I'm being less formal, I can call this portion just the outside. Okay, and then if I'm looking at the portion of that larger secant segment that is inside the circle, I already have a name for that, right? We call that a chord. A chord is any segment that has its two endpoints on the circle. So this is a chord. Okay, quick little recap. So a tangent line has 1 point of contact with the circle, 1 point of intersection. This is a point of tangency. Okay, if I'm looking at a portion of the tangent line, so a portion that connects that point of tangency to a location outside of the circle, that is a tangent segment. Okay, this line right here has 2 points of intersection, here and here. That's a secant line. And if I'm focusing on this outer point of intersection and this point outside the circle, that is a whole. That is the whole secant segment. If I look at my secant segment, break it up into the two parts. This is the part that's outside the circle. That is my external secant segment. and my portion that is inside the circle, that is a chord. Okay, so now we're going to take on two relationships today. Let me slide up. All right, segments formed by tangents. So before I go into this relationship, I'm going to draw another picture off to the side and just remind you of something that we've already discovered. So I'm going to draw the same kind of visual that I had on the left. I'm just going to mark those 2 points of tangency here and here. Okay, so now what I'm going to do is I'm going to connect those 2 points of tangency, right? I have here, I have a tangent pathway, I have another tangent pathway because it's touching the circle in the one location. So if I connect those points of tangency like so, just like that, I know that right here, this angle, it has to be half of its intercepted arc, and I know that this angle has to be half of its intercepted arc. So I may not know exactly what those measures are, but I do know that they're related. I know that they're going to be exactly the same. So if this one was 40 degrees, this would be 40 degrees as well. If this was 60 degrees, this would be 60 degrees as well. So what I essentially have here is I have an isosceles triangle. And if my two base angles are congruent, I know that these two legs, they would have to be congruent as well. So when I'm looking at a circle that has two tangent pathways, and I'm focusing on where they cross through each other right here, I know that this tangent segment right here and this tangent segment right here, they're going to be the same. They're going to be congruent. Give a little tick mark here and here. So here I know that my tangent segment will be equal to the other tangent segment. So in this scenario, the measure of AC will be equal to the measure of AT. All right, so a few examples. This is usually as easy as it's going to get. It's our favorite relationship. We like the basic ones. All right, so for my first one, I'm saying, well, what's Fi? Well, I'm telling you that Ig is 12, so like I said, easy peasy. This one has to match, also 12. I have a tangent pathway. I have another tangent pathway. So this tangent segment and this tangent segment, they have to be the same. Okay, over here, I've just made it a little bit more elaborate. Ultimately, this is what I'm solving for. I want the measure of RA. So if I look at my picture, I see that I have these two tangent pathways, and I know that a tangent and a radius are always perpendicular, so I could draw in that right angle in those two slots. I can also see that, oh, I actually have 30, 60, 90 triangles, so I can fill in those 30-degree angles. So let's say that I focus on just this triangle, this right triangle, this special right triangle right here. I'm going to draw it off to the side. So here's my 30, here's my 60, and I know that this is 12. So I know that my short leg, so opposite the 30-degree angle, smallest side, short leg is X. Opposite my 60-degree angle is my longer leg right here, X root 3. And opposite my right angle is always my hypotenuse, so 2x. So if x is 12, then I multiply by the square root of 3 right here, so 12 root 3. And then right here, if I take the 12 and I multiply by 2, this would be 24. Okay, what I really needed was this part right here. I needed this to be the 12 root 3. And then again, since I have a tangent segment and a tangent segment, they have to match. So the measure of RA is 12 times the square root of 3. I like the answers as simplified radicals. All right, please take a moment and flip it over. Okay, here we're looking at the relationship between secants and the segments. So we're looking at how does this secant segment, how does it relate to this secant segment? Okay, so what I'm going to have you do now is I'm going to have you label this whole secant segment So right here, from A to B, right, that's the whole secant segment. So I'm just going to write W for whole. Okay, and then I know that from R to A, this is the outside portion of it. So I'm going to label that with an O for outside. Okay, for the bottom one over here, there is the whole secant segment. So I'm going to do the same thing. That's the whole. Then the portion that is outside, I'm labeling that with an O. Okay, so now, before I do anything, I want to show you the relationship and where it comes from. So what I'm going to do next is I'm going to draw a little circle off to the side. And I'm going to draw in those two secant segments like so. Just like that. Okay, so go ahead and please do the same. Okay, and then what I'm going to do next is I'm going to make triangles out of those. So I'm going to focus on connecting like this. I'd like you to do the same. And then what I'm going to do is I'm going to make a triangle like so. And I'm going to draw it off to the side. I'm going to draw that triangle just like this, off to the side, what I have in green. Okay, and then I'm going to draw in this segment right here, like that. And I'm making a second triangle right here in purple. So I'm going to draw that triangle off to the side as well. Okay, so we should have our two triangles. If you need to pause to make sure that we match, totally fine. So again, right here I have this triangle in green. That's what I drew here. And then I have this triangle in purple. That's what I drew right here. So I'm trying to think, well, how are those parts related? Well, I do know that this angle right here, it's the same angle for both of them. So if I give a single tick mark here, I can give that same single tick mark here as well as here. Okay, and then I can look at this angle right here. Let me block this out for a moment. This angle has this intercepted arc. I may not know what its measure is, but I know it's half of this intercepted arc. And this angle right here, it has the same intercepted arc. So I may not know what its measure is, but I know it's half of its intercepted arc. So these two angles here and here, they have the same intercepted arc. They have to have the same measure. So I'm going to add those double tick marks to my diagram here and here. So what we should see right now is that, oh, well, these are two triangles. They're similar by AA. So similar by angle, angle. And remember what it means to be similar. It means that they're going to have the same shape, but different sizes. All of their corresponding angles, they're going to match perfectly, but their corresponding sides are going to be proportional. Okay, what I'm going to do next is I'm going to label this part right here as the whole. Let's say it's the first one. And then over here, this was the outside of the first one, like that. And then I'm going to, for the second one, say that this was the whole. So I'm saying whole 2. And for this part, the outside, outside part 2. So then I'm going to add that to my picture. So I can see that for my green triangle first, so I'm just looking at the green triangle right here. This is the whole from here to here. That is the first whole. So whole 1. Okay. And then if I look down here, this side right here, that's from here to here. That is the outside of the second one. Okay, and now I'm going to look at the purple triangle. So my purple triangle is here. So I can see that right here, here is the outside of the first. And here is the whole of the second. So when I'm thinking of, well, how are they related? So I know that this portion right here, in between the single and the double, will correspond with this portion right here, in between the single and the double. Okay, just as up here, this segment, It's in between the single and the unmarked angle, will correspond to this segment right here in between the single and the unmarked angle. So if I was to build a proportion, I could say that hole 1 is to hole 2, just as outside 2 is to outside 1. So there's my proportion, and if I cross multiply, I end up seeing hole 1 times outside 1, right, that product, is equal to hole 2 times outside 2. And that's our formula. That's going to be our whole formula. So it's going to say the whole times the outside is equal to the whole times the outside. Let me box it. Okay, and if I go up here and I add those little sub numbers, here is my hole 1, my outside 1. Here was my hole 2. Here was my outside 2. So often you'll hear me just say hole times outside equals hole times outside, and I don't add in those little sub numbers. I often just write it like this. Hole times outside equals hole times outside. So if I was applying it to this diagram, my hole here would be BA, that measure times the measure of RA would be equal to this hole, NA, times this outside region, which would be IA. All right, so now we have some problems. So again, when we have two secants, hole times outside equals the hole times the outside. Okay, so let me push it up. All right, so I'm going to label what's given. We're told that RS, so from here to here, that is 5. We're told that RT, so here to here, is 18. We're told that RQ is 8. And we're asked to solve for RP. So that whole measure, RP, I'm going to call that X. So here, let me just lay out my structure. Whole times outside equals the whole times the outside. So if I look at the one on top, here is my whole, X. Here is my outside, 8. So I'm saying X times 8. And down here, my whole is 18. And my outside is 5. Okay, so when I multiply, I get 8x is equal to 90. And then I'm just solving for x. So I'm going to divide by 8. And I get that x is equal to 11 and 1/4. So the measure of RP is 11 and 1/4. I could write that as 11.25. That would be perfectly fine. All right, next up. So in this second problem, we are told that EF here is 8. We are told that DE from here to here is 10. And we're told that FH here to here is 16. And we're asked to solve for FG. I'll call that X. So again, just laying out my framework, whole times outside equals whole times outside. So my whole part for the top one, my whole part is actually the 10 plus 8. Right? This whole part here to here is 18. So I really have 18 times 8. Here's my whole, here's my outside, right? It's outside the circle. Equals here is my whole, 16, and the outside is x. Okay, so now I have 144 is equal to 16x. Divide each side by 16, and I get that x is equal to 9. So the measure of FG right here, that is equal to 9. All right, next up, it's going to get a little harder because you know I love to infuse some algebra into the skill. So here we go. So in this one here, AB is 3. So right here is 3. And we're told that AC, A to C, this whole part, DE, so D to E is 5, and we're asked to solve for AD. So right here, that is X. So again, laying out my framework, whole times outside equals whole times outside. So on this left-hand side, here is the whole is 12. And then the outside here to here, well, that's 3. Okay, over here, I need the whole. So the whole is adding together the X and the 5. So I have X plus 5 as my whole. And the outside is what I have defined as X. All right, so now cleaning it up, I have 36 is equal to, I got to distribute that X. So I get X squared plus 5X. Right, it's a beautiful quadratic equation. We know our options for solving it. We could solve by taking the square root, we can try to factor, we can use quadratic formula, we can complete the square. So for this one, I know first off, make it equal to 0. So before I even think further, I need to take away that 36 from each side. 0 is equal to X squared plus 5X minus 36. So if I run through my list, could I solve this by taking the square root? I can't do that because I have a linear term. That blocks me from using that method. Second method, does it factor? So if it factors, I'm looking for two numbers that multiply to a negative 36 that add to a positive 5. So take a moment, maybe pause for a moment, and factor this. Okay, then unpause. This is going to factor into X plus 9 times X minus 4. And if I set each factor equal to 0 and I solve, I get X equals negative 9, and I get X equals positive 4. And if I try the negative 9, if I plugged it in, say, right here, that would make no sense, right? I can't have a negative distance. I can't have a negative measurement. So this answer does not work. The only one that works is an X value of 4. And then it's saying, what is AD? Well, AD is 4. Okay, one more variation. So for this one, we are told that SP, so SP right here, that is 12. NI is 3. IA is 5. And we're solving for SA. We want this whole portion, that is X. So I know that I'm doing whole times outside equals whole times the outside. So up here, my whole is X. That part's clear. But my outside is this portion right here. So if I know that this is X and this is 12, well, this part right here would be X take away 12. X take away 12. X minus 12. So the outside is X minus 12. Over here, the whole, I have to add up the 3 and the 5 to get 8. And then the outside is 5. Okay, so here I have to distribute the X. I get X squared minus 12X is equal to 40. So again, I see another quadratic equation. I want to first make sure that it's equal to 0. So I'm going to take away the 40 from each side. So X squared minus 12X minus 40 is all equal to 0. Okay, so now here, if I run through my list, can I solve by taking the square root? Well, no, that's not going to work because I have a linear term right here. My next option, can I factor it? Can I think of two numbers that multiply to negative 40 that add to negative 12? I can't. I get stuck. So I have to go back and think of another option. And that option right now is going to be using the quadratic formula. So the quadratic formula, just to remind you, big Algebra 1 skill. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And in this problem, the a value is 1. That is the quadratic coefficient. The b value is negative 2. That's that linear coefficient. And then the constant is the c. So the number at the end, negative 40, that's the c. So from here, I'm just plugging it in, and I'm just cleaning it up. So here, I'm just going to follow my work You know, I love an arrow. I'm going to go like that. So up here, x equals, so negative b, so it'll be 12, plus or minus the square root, negative 12 squared. So I'm going to say that's 144, minus 4 times a, which is 1, times c, which is negative 40. Let's see if I can make all that fit. There we go. All over 2 times a, so 2 times 1. So x equals 12 plus or minus the square root of 144. And again, I usually see a mistake happen here. This is where I see a little sign error happen at times. So that is a product. So if I multiply negative 4 times positive 1 times negative 40, I get plus positive 160 all over 2. So 12 plus or minus the square root of 304 divided by 2. So now it's really just a matter of, can I simplify that square root of 304? And I can. So when I look at this, I see, oh, well, if I made a little factor tree, let me see where I have room. So if I go up here and I look at the square root of 304, okay, so I can say, well, that is actually 16 times 19. So if you can see that quickly, that's great. If not, you can break it down with 2's and keep breaking it down from there. So I was able to see, oh, well, that's 16 times 19. There's my pair of 4's. That 19 is staying behind. So it simplifies to be 4 square root 19. So next stage, I have x is equal to 12 plus or minus 4 times the square root of 19, all divided by 2. Okay, and when I'm simplifying from here, I need to find a number that goes into all 3 of these terms. So they're all divisible by 2. So if I divide each of these 3 parts by 2, I now have 6 plus or minus 2 square root 19. It would be all over 1, but I don't write the over 1 part, right? I don't write 4 over 1. 4 over 1 would just be 4. So here's my answer, but this is really 2 answers, right? Because I'm solving a quadratic equation. So my 2 answers, I have one that's 6 plus 2 times the square root of 19, and the other is 6 minus 2 times the square root of 19. So let me show you what happens when I type into my calculator 6 minus 2 times the square root of 19. So before I even hit enter, I can conceptualize what I'm going to get as my answer. I know that the square root of 16 is a little below the square root of 19, and the square root of 16 is 4. So this is going to be 6 minus 2 times something that's a little bit more than 4. I'm going to get a negative number right here, and I get negative 2.72. And I know that a negative number in this context, it does not work. I can't have this part being a negative number. I am only interested in the positive. So my answer would be 6 plus 2 times the square root of 19. That would be my exact answer in terms of a simplified radical. If I wanted to see what it is as a decimal approximation, so an approximation, because it's no longer precise, it's a rounded answer, I would get that x is approximately 14.72. I will always prefer a nice, precise answer. I want to see it the way that I boxed it right here. All right, that is our lesson for today. I hope you guys are doing well. All right, have a good rest of your day.